Hello, friend. My name is Derek Harder, and in this video, we're going to continue our discussion about the transformer architecture. So, in particular, previously, we went through some necessary background to hopefully that you can develop some of the concepts you need. So, we looked at neural attention, a little bit about how that might actually be implemented. And then we talked about the multi-head layer that Keras provides, which is the kind of the mechanism that implements the neural attention, self-attention mechanisms that we talked about. So in this video, we're going to turn towards looking at the transformer architecture. So we'll look at the transformer encoder. So originally the transformer was built to be a sequence encoder, so it would translate input sentence in one language to an output sentence in another. Okay, so it had an encoder and a decoder, and that will be the example that we will use later on. But in this video, we'll concentrate on the transformer encoder and its basic architecture and how you can use that for classification. Okay, so let's get started. So roughly, you can think of the architecture of the transformer encoder like this, okay? And we're going to implement this as a custom layer, reusing multiple layers inside of it. So if adding extra dense projections in the multiple heads in our previous discussion of the multi-head layer is so useful, why not also do that to the output attention mechanism, okay? So we're going to factor the outputs into multiple independent spaces. That's essentially what these dense layers are doing here in the model. And then the other ones are things that we talked about previously. So, we might also want to add in residual connections because things are starting to get big here. We want to make certain that we don't suffer from vanishing gradients. So there's several places in the architecture we'll look at for a basic transformer encoder where we have these skip or residual connections. So we have one here where we go around preserve information that's happening from the basically the attention mechanism that we're going to use, and another one around these dense layers that is factoring the outputs that we do here. And maybe I should have mentioned before we start, the whole thing is based on the important thing. One of the important things for a transformer is it is using this neural attention, right? So we're reusing the multi-head attention layer in Keras to implement the self-attention mechanisms that we have. And then finally, we talked a little bit about normalization layers previously in this class, right? So it's important to normalize inputs before you train with them, but also it can be found that actually normalizing the outputs of layers can help. So it's thought that this helps by, again, with the vanishing gradients problem. So in particular, there's normalization layers after the result from the self-attention and after the result of these dense layers that are factoring the outputs here. Okay, so with that description of the architecture, we're going to actually implement this as a custom Keras layer. My understanding as of making this video, the transformer architecture, transformer encoder and decoder haven't quite made it into the Keras API. Maybe it's getting there, so it is available in, we'll see here, in kind of a submodule, I think, that are used to test out stuff before they get moved into the official one. So for now, so let's try building basically a custom layer to implement the encoder, that architecture that we just looked at. Okay, so we've seen examples of building custom layers before. So we have an init method. Basically, in the init method here, we're creating those layers that we talked about. So we have a multi-head attention layer that we're going to use. We haven't connected them up yet. Before I get into these, so we add 3 extra parameters for our constructor, the embed dimension for our word embedding that we're using, the dense dimension. So this is just the size of the inner dense layer for the dense projections that we're going to use here, and the number of heads. So for the multi-head attention layer, the number of those independent heads that we wanted to create when we do that, right? So we create a multi-head attention layer that we're going to use using that number of heads. We also have to tell it the embedded dimension of the stuff that comes in and goes out of this. Our dense layer, where it's just a sequence of two dense layers here, and we use that dense dimension parameter for one of these. And then we're going to have a couple of these layer normalizations. So I realize I have to talk a little bit more about these. So we looked at batch normalization. So we have to use something called layer normalization, which is similar, but what you should use for when you're doing sequence data coming in. So you look, the call function basically put these together, right? So it will get the output by sending the input into the attention layer here. Okay, so I had to pause there because I just noticed that for the attention layer, we only pass in the two inputs. So it turns out that the three inputs when you're doing a call are query value key, but the third one, the key, is optional. So if you don't provide that, it uses the value, both for the value of the key. So that's why it's not 3 instead of 2 when we're actually calling it with our inputs that are coming in to do the calculations that the attention does and get the output. Another thing, so we talked about masking in recurrent layers here. So we are using masking again in our custom built layer here. So we have to get the mask and kind of pass that around where it's needed. So the output from the attention, notice we're doing our residual connection here. So the original inputs gets combined with the attention outputs. That goes into our first layer normalization. And then that goes into the dense projections, right? And then again, we have another residual connection where we take the projection, the dense layer output with the input that was coming into it, and combine those, and that's the resulting output from our last normalization. Okay. And I believe we've talked about this before. So when you're, when you're building a custom class that's subclassing the layer, there's certain things you have to add. So if we want to allow it so we can save a model, we have to have a get config method that will add to the dictionary any additional parameters that are used in the constructor. So our embedding dimension, the number of heads, number of units in our dense dimensions here. So so just a little note, we're using layer normalization instead of batch normalization. So when I talked about normalizing between layers, we probably talked about batch normalization before, so I've forgotten that. So you really shouldn't use layer normalization if you're doing sequence models because it normalizes each sequence independently, so it won't kind of destroy information in your sequencing. So batch normalization won't work well for sequence models. So just real quickly, I mean, the only difference between these two examples is kind of in pseudocode of what a normalization does a mean and variance, but it does it on each sample independently. So by just doing this where you pass an axis -1, the result here where we're having like 64 samples that are sequences that are 600 by 100 dimensions, you get the shape of the mean and variance that are done here. So this is really doing this on every 64 by 600, doing on every value in the sequence independently. Whereas batch normalization does that kind of over the whole batches. So if you look at this, the shapes of the mean and variance here, if you're using the first 3 dimensions are, so you basically only got one mean and one variance for each one. In this case, I did it as if it was like a set of image data. So you might use batch normalization for image data. So you've got just one mean for each one of the 3 channels for all this data. So, now that we have this custom transformer encoder layer, we can try it out, see how it works. So we're first gonna do it on a simple classification. So we're doing the same classification we did previously. So we're using the IMD database that we vectorized by hand, and we're going to do a sentiment analysis, so encode it into positive or negative review in this case. So it's really kind of a binary classification, right? So we still need, for our inputs, we need to get an embedding layer. We're going to train an embedding layer on the fly while we're doing this. Have it use 256 embedding dimensions, but we're going to feed that into our custom transformer encoder. So we've got embedding dimensions of 256. We want to use 32 outputs on our dense dimension, and just use 2 hits. Okay? And adding a little bit more regularization, so some dropout and some other things here. All right, so let's train that and see how it does. So this is what our network looks like, but we've got a bunch of stuff hidden inside of our custom transformer encoder layer here. All right, so let's go ahead and train it. Okay, so when that finishes, take a little bit of time, but let's load it back in. So the best model by loss, and try out the on the test data as usual here. So I mean, you'll find that it doesn't improve on our best bag of words model that we used before. So you usually get about 87% or so on the transformer architecture. This is kind of a side note. There is an implementation of the transformer encoder in this project called Keras Hub. So I guess that Keras Hub is it was mostly for pre-trained models, but it has stuff in there that's not in the main TensorFlow Keras. So it's kind of an extension of the core API that provides models, and it also provides different of these layers, right? So you probably would want to use that rather than using a custom layer like we did here. But you do have to install Keras Hub, so usually I would do like a pip install on Keras Hub to get that. But it's used pretty much the same way as our custom layer, except that you don't have to provide the embedding dimension. So presumably it infers that from the input coming into it. So we probably could have done that on our custom layer as well. So it may look exactly like the one from the Keras Hub layers here. I'll go ahead and run that. It'll probably take about the same amount of time to run this one here. Okay, so when that's done, if you evaluate on your tests, you'll see that basically usually we should get about the same performance that we did before. If you look at the output on the loss and the accuracy, pretty much similar, if not exactly the same as our custom built layer. Okay, so at this point you may feel a bit uneasy about the results, maybe even a bit cheated. So isn't this aren't sequence models supposed to be able to beat bag of words models, so especially this new transformer encoder architecture? So we're not getting as good as our best simple bag of words model. So another thing that you might not quite realize, so we started off the discussion of all this by highlighting the importance of word order. And another thing that was mentioned in passing is that the transformer was a sequence processing architecture originally developed for machine translation, and yet you may not have noticed, but the encoder we just created isn't a sequence model at all. Okay, so if I can go back to the architecture here, so looking at the architecture, the multi-head layer. We presented the pseudocode as having a loop, but it really processes the inputs when it's doing the attention all at once as batches. Okay, so it calculates the attention scores, but the result is all the inputs get recoded in the encoding space, so shifted slightly. So they come in as a full sequence and go out as a sequence. And these dense layers, so they are taking in. So each sample in a batch would be, in our examples, would be 600 sequence length and an embedded dimension of 256. But it really flattens those and processes those in the dense layers as all flat. Okay, so I mean the multi-head attention layer is really looking at tokens in a sequence as a set. It's not really doing the same thing as like a recurrent layer does. And the dense layers definitely aren't doing any kind of recurrence, okay? So you could change the order of the tokens and it wouldn't matter to this most recent architecture that we did with this transformer encoder, okay? So why do we say that the transformer is a sequence model? So how could we possibly claim that, right? So if you go back and kind of list these out as like a table of the different sort of models, bag of words, like using either bigrams or unigrams, or using recurrent models. So, the bag of word models are not really aware of word order. And they don't have any of these self-awareness. So they don't have any context in them. So you can think of bigrams or trigrams of giving a limited sort of word order awareness. Recurrent layers, I suppose we could add in like an attention layer, but recurrent layers, the way we've used them so far, they are aware of word order. So they explicitly, conceptually, are iterating over the sequence from the first value in the sequence to the second one up to the last one. But the way we've used them, they don't have something like a multi-head layer, so they don't do any neural focus on the data coming in. Right? So self-attention by itself with the multi-head layer in our transformer that we've done so far really didn't have word order awareness, so it was really still treating the words input as a set. Okay, so again, how can we claim that the transformer architecture does have word awareness? And the way that we do that is we're going to inject positional encoding. So normally another piece of what we think of as the defined transformer architecture is we add in positional encoding for our transformer layers. So again, we'll create a custom layer to do this position embedding, kind of show conceptually how it works. There is also like a position embedding in the Keras Hub. I don't think I'll run that one this time. So the idea here that's being done is we're actually going to modify the embedding layer to do add in this positional embedding idea. And so, I don't see any reason why we couldn't try this in front of like a recurrent layer if we wanted to, that was taking embeddings coming in. But in this case, so for this custom class where we're doing positional embedding, we'll have just a regular embedding layer like we had before that's going to do the token embedding. So, we'll use like 256 dimension. It's one of the inputs to this custom layer. So we have two extra parameters defined for the constructor here. And then we need the sequence length because we're going to input just a sequence and it's going to learn embeddings here. So we could just use like just an integer index for our sequence embeddings, but that doesn't work very well. So we do need to learn kind of a new embedding in the same way we do it for tokens, but we'll learn it for this positions for our sequences here. Okay. So all that happens is, we have a graph that we take the inputs, so the token embedding layer does the same thing that our embedding layer did before. So it's doing the same thing as before. But what we pass into the embedding position is just a input that has a range of values from 0 up to the length of our inputs here. Okay? So we pass that into the embedding position, and then we just combine those. And that's the result from calling this layer. Okay, I mean we are doing a mask here, and since our custom layer has some extra parameters for the constructor, we have to have a get config method if we want to save this model. So if you put it together, the only thing it changed from our previous use of the transformer encoder is we use this in positional embedding layer. So it's going to be returning extra information about the position into the transformer. So that makes the overall architecture here kind of position aware. Right? So again, we'll find that this doesn't help us on performance, and we'll talk about that next as a final thing in this video once we're done training. Okay. When that finishes, we'll go ahead and just run it with our test data as usual. Okay, let's see if we can load and run that. So yeah, I'm getting some warnings about build. Probably need to go back and look. I think the API changed a little bit, so probably some of the stuff we're doing in call really should be done in like a build method, I think. So, but anyway, the point is that you'll get an accuracy around 88%, which is maybe better than the previous one without positional encoding, but still not as good as sort of our best bag of words approach. Okay. So I don't think I'll show again the Keras Hub. Actually, I will mention one thing real quickly, that the position embedding, it looks like in the Keras Hub, doesn't do the token embedding in parallel with the position embedding. So I think the correct way to use it is to, you have to have a regular embedding layer for the token embedding, and then use the position embedding after it, if I read the documentation correct. So I'm not going to show the result of that running here. So that's basically it. But one last quick thing here. So the author does have a little discussion about when to use sequence models over a bag of word models. It's not true, and the author is definitely right on this too. If you hear people saying that you really should be using a sequence model or a transformer, that won't always work the best. So the dividing line really is you kind of really need big data for transformers and sequence models for recurrent layers to work well. Okay, so you need to adequately have the input space sampled, or else you'll have problems. And so in that case, usually a bag of word models will work better. So a small stack of dense layers with bigrams was probably the thing that was working the best with our IMDb sentiment classifier here. So the author of our text, Dr. Cholet, gives kind of a word of rule of thumb thing you can use. So the ratio between the number of samples total that you have in the data to train with and the length of your samples. If that's kind of big, then sequence models are maybe going to work for you. If that's not very big, maybe a bag of words with some positional encoding using like bigrams or something will work best. Okay. So that's it for this video. So just to quickly summarize everything that we actually went over in the previous video and this one on neural attention and the transformer architecture. So this is kind of an important sequence of videos if you're interested in generative AI and like large language models and things like that. So neural attention is something you should try and at least learn the basics of so you can understand it intuitively. So it can be used to build powerful sequence models that don't feature recurrent layers. Okay, or by that I mean that it can be used to build models that will work on sequence input data without any recurrent layers. We can make features context specific by computing attention. So that's kind of what neural attention does, is it adds in context to the word embedding representations. A smart embedding space provides different vector representations for a word depending on the other words around it, right? So it'll take into account the context and modify all of the vectors in a sentence or in a sample based on that context, and that works much better. We didn't have good examples of that with this data set, but that can work much better in lots of settings. The multi-head attention layer is the thing in Keras that implements this sort of context-specific neural attention. It takes 3 inputs because it's based on the most general version of the attention mechanism, where you have a key query value, 3 kind of inputs. The TransformerEncoder uses multi-headed attention as an input, and it factors those outputs into multiple independent spaces, and it has residual connections and normalization layers and things like that. So that's the basic definition of the TransformerEncoder architecture. But yeah, so don't discount bag of word models with bigrams. They're still a good choice when you don't have enough samples, or your simple sample lengths are kind of really large. And sequence models, including transformers, work best with large data or small sample sizes. All right, so that's it for this video. I hope that was useful for you, and I hope to see you again in our next video.